Hi everybody, welcome back. This is Unit 10, Lesson 2, and we're in Section 3 of our notes. We're going to talk a little bit more about those energy hills that all chemical reactions have to get over in order to react. So what these energy hills are really called are potential energy diagrams, PE diagrams, if you will, okay? And what potential energy diagrams show are the changes in energy that occur as a reaction proceeds. So on your y-axis here, you'll have potential energy or stored energy. And on your x-axis, you'll have the progress in the reaction. Sometimes that's labeled time. It really doesn't matter, but at times it's labeled time. Before a reaction begins, what you'll notice you have is your reactants. You have your ingredients. Nothing's happened yet, okay? And those reactants, due to their chemical bonds, have a certain amount of stored energy in them. At the end of the reaction, you've made something new. You have those things that we call products, okay? The reaction does not begin until you have sufficient energy to get to the top of the hill. So this is the point where the reaction begins, okay? And when the reaction begins, you don't really have reactants. They started reacting. You don't really have products. You're not done with the reaction yet. You have something in between. And what that something in between is called is the activated complex. So you need to know those basic regions of the potential energy diagram. And there are two different shapes of these diagrams that you will encounter. I call these the fun sledding hill and the not so fun sledding hill. So we will always begin here, okay? We'll always begin at time 0 or before the reaction begins, okay? You can tell in this curve that if you're starting here, you have to walk all the way up this hill before you can slide down. So that is really not so fun because you have a big trek up the hill and then only a little bit of weed, right? This is all energy that you have to put in. Shh. And this is energy that comes out. So you can see in this curve that the energy you have to put in is greater than the energy you have coming out. This is the not fun sledding hill. That's a long way to walk up for only a little bit of weed, okay? And the not fun sledding hill depicts an endothermic reaction. More energy going in than coming out, okay? This shape next to it is the really fun sledding hill because you start here and you only have to walk up this far. And then look at all the weed that you get going down there, right? So this is your energy going in and all this, so you just have to put in this little bit of energy, and all this is the energy that comes out. So you can see in this circumstance, you have a lot more energy on the fun side, a lot more energy coming out than you have to put in. And if you have more energy coming out than you have to put in, that's an exothermic reaction. That is the fun sledding hill. So these potential energy diagrams will be one of these two shapes, either endothermic. I think sledding has 2 Ds. Or endothermic. Okay, exothermic is the hill you want to go down. Endothermic is the not so fun one. Okay, there are 6 things you're going to need to label on this curve. I have the 6 things described in your notes on your paper, but I'll walk you through them. There are 3 potential energies. If you notice my little thing over here, there's 3 potential energies you have to label. There's 2 activation energies, and then there's this thing called delta H. Okay? So, if you remember, this is before the reaction begins. This is during the reaction. And this is after the reaction's over. Okay? Before the reaction begins, all you have are your reactants. So this line right here is your reactant line. And the potential energy of your reactants can be represented with an arrow that goes from the x-axis to the top of that line. So we can see that the reactants have 200 joules or whatever of energy. If we wanted to draw a line to represent that, we would go from our reactant line all the way to the bottom of the curve, okay? So this represents the potential energy of your reactants. It's the amount of energy the reactants have before any reaction begins, okay? At the end of the reaction, all we have are our products. So this line right here represents your product line, okay? And we can see the products have more energy. This is the not so fun sledding hill, right? You got to walk all that way up and you only get a little bit of weed. So this is an endothermic reaction because it's the not so fun sledding hill. Okay? The products have about 350 joules of energy. So if I wanted to draw a line to represent the amount of potential energy of my products, it would go from the x-axis all the way up to the product line. This is the potential energy of your products. Okay? So notice both of these potential energies start at the x-axis. They just end in different places. The first one here ends at the reactant line. The second one ends at the product line. Okay? It really doesn't matter where I draw this, left to right. It only matters where I draw it top to bottom. What I mean by that is if I wanted to be tricky, I could draw a line over here and call that the potential energy of my reactants. Because if you notice, it starts at the x-axis and ends where the reactant line is, okay? So don't really look left to right for these to identify them, look top to bottom. Because what they're going to do is give you this diagram with a bunch of lines, and you'll have to identify which ones they are. Okay, so watch for that little trick. The third potential energy is the potential energy of your activated complex. Remember this, not reactants, not products, something in the middle. That is your activated complex. And so if we can see the activated complex has 450 joules of energy. Again, if I wanted to draw a line to represent that 450 joules of energy, it would start at my x-axis and go all the way to the top of the hill. All right? That's always the longest line on your curve. It is the PE of the activated complex. Sometimes I abbreviate that AC, the PE of the AC. So any line that begins at the x-axis is a potential energy. Wherever it stops, that'll tell you what it is. If it stops at the reactant line, PE of the reactants. Stops at the product line, PE of the products. Stops at the top of the hill, PE of the activated complex. Okay? So we've taken care of the first three things here that we need to label. Okay? I believe in our notes we have some information to fill in for one of those. Is it the PE of the AC? Where is it? Yes. Okay. So if the reaction's endothermic, remember that is the not so fun sledding hill, then the peak potential energy of the reactants is less than the potential energy of the products. If we have the fun sledding hill, right, the potential energy of the products is smaller. This is your products, this is your reactants. The potential energy of the products is smaller. The potential energy of the reactants is greater than the potential energy of the products. Okay? And I think we're okay there, so we filled that in. All right, let's go back to our curve and label the three remaining things that we have to label. The next two are activation energies. What's important that you know, make sure you're listening, is that activation energies do not touch the x-axis. Activation energy is the additional amount of energy you need to add to get to the top of the hill. Okay? So, when we go forward, left to right, like we're reading, that's the forward direction. When we go this way, burp, that's forward reaction. When we go backwards, that's reverse. So when we proceed forward, this is where we start. We are here. We will not react until we get to the top of the hill. So if we're starting at 200 and we need to get to 450, we have to put 250 more joules of energy in. That is your activation energy forward. You're starting here, you're going there, right? That's the activation energy of the forward reaction. I'll write it out this time. Okay? What that numerically would be in this example is about 250 joules, right? Because you're starting at 200, that's what they already have, and you have to get to 450. So I would have to supply 250 more joules of energy to get the reactants to react. Okay? If you're going backwards, you're starting here and going that way. So when you're going backwards, you want to turn your products into reactants. Your products have 350 joules, and to go backwards, you need to get to 450. So when we're going reverse here, that's how much energy we need to put in. That's your activation energy of the reverse reaction. Okay? So we're starting at 350 and ending at 450. That means we have to put 100 joules in this example of energy in. Okay, so sorry about that. That is your activation energy of the reverse reaction. Notice it's smaller. And then finally, what we have to record here, and then we'll be done with this video for tonight, is this heat of reaction. Heat of reaction is the difference between the potential energy of the products and the potential energy of the reactants. It's the difference between those two lines. So what is unique about the delta H, or the heat of reaction, it's also called enthalpy of the reaction, is it doesn't touch the top of the hill. If you notice, the activation energies start at the reactant line and product line and go to the top of the hill. It doesn't touch the top of the hill, and it doesn't touch the x-axis. It is the arrow that hovers in the middle. It is the difference between the product line and the reactant line, okay? So if I'm drawing it here, I'm going to draw it in red. I might draw it from here. It doesn't seem to really touch much, right? It goes from the reactant line, or where the reactant line would be, to the top of the hill. That's your delta H right there. That's your number 6. And I think we have a couple things to fill in for delta H. Okay? Delta H here is also known as heat of formation or heat of reaction. It's the energy difference between the products and reactants. So it's the difference between the reactant line and the product line. We can calculate it with this equation if we have numbers. Like in this last example, we have numbers. I'll show you what delta H would be in just a minute. If the reaction's endothermic, delta H is positive. If the reaction's exothermic, delta H is negative. That makes sense. If delta H is positive, you really gain energy, right? Than what you had. If delta H is negative, you are losing energy. Okay? There is a reference table for a bunch of different processes. Notice it here. It's table I. So they give you a reaction in table I, and then they give you the delta H. This negative would simply just indicate that it's an exothermic reaction. That much energy comes out every time that reaction occurs. If you ever forget delta H is negative, right at the bottom, I kind of clipped it in here, there's a little asterisk that says minus sign indicates an exothermic reaction. So you really don't have to memorize that delta H is negative for an exothermic and delta H is positive for an endothermic, because it tells you right at the bottom of reference table I. Okay, so this is on table I. You just have to know, of course, as usual, where to look. So let me show you in that last graph what the delta H quantitatively would have been. We could have gotten it. Okay? As I told you, delta H is the difference between your products and reactants, right? Delta H is the difference between the potential energy of the products, and it's always P minus R, minus the potential energy of the reactants. Do you remember our products had 350? In this example, and our reactants had 200. So the delta H here is 150. And it's positive, as it should be, because we said earlier that this was endothermic. So delta H is positive for this reaction because the products have more energy than the reactants. All right, everybody, that's it for tonight. We'll see you tomorrow in class. Have a great evening and stay safe. Bye-bye.